Okay, welcome to the LONCAPA explanations. Okay, so for this question, we have a river that's flowing and a person traveling upstream. So let's say this is up, this downstream. So this person's traveling that way, and the river flows that way. That's river and the person. So let's let the river's velocity is going to be, let the river's velocity equal VR, and the person's velocity we'll call VP. Okay? So let's draw it out real quick. What's the scenario? Here we have a motorboat of a person traveling 1.24 kilometers upstream. So the person travels this way for 1.24 kilometers. And then they pass by a log. So there's a log here. Maybe I'll draw the log with another color. There's a log here going this way. At the same throttle setting, the boater continues to travel upstream another 66.9 minutes. So 66.9 minutes after it passes, and then it turns around. Let's pretend there's no time of the turn, but that's just for visual. And it turns around and it comes back. Okay. So we have one scenario here, two scenarios there. So the first scenario is where it goes the 1.24 kilometers. Second scenario is where this boat is going upstream, and for the 66.9 minutes. And the third scenario is when it starts going downstream, because now it's following the stream, so the velocity will increase. And then we have the log scenario, which is in red there. So let's start with the person. In scenario 1, we know that we have the person's velocity is just VP. So V equals VP. We'll say V1, 1 for the first scenario. We have distance equals 1.24 kilometers. And we have time equals, well, we don't know what time is, so time is just T1. After this, we have scenario 2, where velocity 2 is equal to, we don't know. Well, velocity 2 is equal to VP once more. And actually, in velocity 1 and 2, VP is the speed of the motorboat, but the velocity is actually the speed of the motorboat minus the speed of the river, because with velocities, they're vectors, right? So they add up. So if you have VP going this way, VR going that way, they'll cancel out. Okay. We have our time, which is 66.9 minutes, which I'll turn into hours just by dividing by 60. So we have 1.115 hours. And we have our distance. So time 2 and distance 2. What is our distance equal to? Well, we know d equals d over t, so d equals vt. So it equals 1.115 vp minus vr. Then we have scenario 3, where it turns around, and our new velocity is VP plus VR. Our time, well, we don't know what our time is. And our distance, we also, distance 3, we just know that our distance 3 is equal to our distance 2 plus our distance 1. And we also know that distance 1 is 1.24 kilometers plus distance 2, which is 1.115 times Vp minus Vr. Perfect. Now, we have to take into account how the log is going. Our log here only has one scenario, where its v is just equal to Vr. So the v of the log is just Vr. V of the log. And we have the time for the log to reach from when it met the boat to reach the end is the same time as t2 plus t3. So equals t2 of the human plus t3, because it meets it right before t2 starts. And we know our distance of the log is equal to 1.24 kilometers. So in this way, we can calculate Vr. We'll set up an equation here where Vr, scroll down a bit, is equal to the distance over time. We also know here that for person 3, we can set up an equation as well, where time is equal to velocity, is equal to distance over the velocity. Okay? And we know what our t2 is already. So now we can plug our t3 in here and our t2 in here. Okay? So let's give us some space. So we know that now Vr is equal to 1.24 over 1.115, because that's t2, plus 1.24 plus 1.115 Vp minus Vr, all of that over Vp plus Vr. Okay, so now let's get the 1.115 to have the same denominator as the other. So we have 1.115 Vp plus Vr plus 1.24 plus 1.115 Vp minus Vr. All of that over Vp plus Vr. And, well, let me shift this down a bit, because all of that is still over our 1.24. We can't forget our 1.24. So now, what do we see? We see some things cancel out here. So the 1.115 times Vp plus Vr, and then on the other side we have minus Vr. So we can cancel these two Vrs out, and we'll end up with 1.115 Vp plus 1.115 Vp. So it's 2 times that. So we'll do 1.115 times 2, and we end up with, we'll start with our 1.4 at the top, 2.23 Vp plus 1.24, all of that over Vp plus Vr. So now we can just rewrite this as Vp plus Vr, all of that over 2.23 plus 1.24. Sorry, I forgot the Vp here. Vp plus 1.24. Okay. So now, let's not forget that this is still equal to Vr. That's what we've been doing. That's what we've been doing the whole time, right there. Okay. So now we can multiply the bottom. So we have Vr times 2.23 Vp plus 1.24 equals 1.24 Vp plus 1.24 Vr, right? If we distribute the VR here as well on the left side, we get that 2.23 VP VR plus 1.24 VR equals 1.24 VP plus 1.24 VR. We see that 1.24 VR is on both sides, so we can get rid of those. Now that those are gone, we also see that VP can be divided out. So we divide by VP, as long as VP isn't 0, but in this case it's not 0. So we get 2.23 VR is equal to 1.24. So we get that VR is equal to 1.24 divided by 2.23, which is equal to 0.556, and we worked in kilometers per hour here. So, back to our question. Our question would be, calculate the velocity of the river, and we let VR be the velocity of the river. So in this case, our answer would be 0.556 kilometers per hour.